So on page 236, they have the graphs of y equals 2x plus 4 and y equals 1/2 x minus 2. The first thing I want you to notice that the blue equation, if I start with the red equation and I solved for x, I could subtract 4 on both sides, then divide everything by 2. And when this whole thing is divided by 2, that means the y is divided by 2, which is the same as 1/2 y. And the negative 4 is divided by 2, which is the same as minus 2. And I want you to notice, the similarity between that, when I switched with x and y, and the blue equation. The blue equation says y equals 1/2 x minus 2. Now, what's interesting about this, when you switch the x and the y, or when you solve for x, and then at the end, if I would switch the x and the y, I would get this equation. What's interesting about this is that if I have something on the red equation, for example, I have the point 1, 6, I could label that right here. This means when you plug in 1 for x, you get 6. The second equation on the blue equation, when you plug in 6, half of 6 is 3 minus 2, you get 6, 1. And same thing with 0, 4. When you plug in 0 into the red equation, you get 4. When I plug 4 into the blue equation, I get back to 0. And if I plug negative 2 into the red equation, I get 0. If I plug 0 into the blue equation, I get negative 2. What this is called mathematically is an inverse, something that undoes something else. And you know a bunch of these. What's the inverse of adding 5 to something? If you had to work backwards, you'd subtract 5. What's the inverse of doubling? Well, you would cut it in half. What's the inverse of squaring something? Square rooting it. So we know a lot of these operations. It's just when you do more than one thing, right? In the red question it says, take something, double it, and add 4. If you had to work backwards, what would you need to do? Well, you'd have to cut it in half and subtract 2. But if you actually work backwards, you might even say it better like this. I would subtract 4 from it and then divide it all by 2. That actually makes more sense when we're talking about it, but if I simplified it, I get this other equation. So what this is called is an inverse. And one of the things that happens when you do an inverse, and I'll draw it in on here, is if I draw the line, the perfect diagonal line y equals x, the one function that undoes the other function is always a perfect reflection over the line y equals x. So in the box here, they have what happens when you reflect in the line y equals x. You get an inverse. And as far as taking out your highlighter and adding something to this, here's some important notation. When the inverse is also a function, we can use inverse notation. And some important little notes that you can put off to the side for inverses. First thing, you can find the graph by reflecting it over y equals x. You can find the equation you can find the equation by switching x and y and solving for y. What does that look like? Well, if my original equation was 2x plus 4, and I switched x and y, I would get x equals 2y plus 4. If I then solve for y, well, I would get x minus 4 equals 2y. Divide everything by 2, 1/2 x minus 2. And the notation for an inverse function is y equals f to the negative 1 of x. So this is the last kind of transformation we're going to look at, is reflecting over a diagonal line, y equals x. We've got, whenever you're switching your x and y, and solving for y, that's algebraically how you can find the equation. Some new notation that we have to know, y equals f inverse of x. And so now we can look at example 1. Here's the graph of g of x. Sketch the graph of the inverse on the same grid. So for A, when you see the word inverse, you're going to go back to those notes that we wrote on the side and think about everything that it means. The key thing is that you're just going to switch your x and y coordinates. And so if on my original graph I have negative 4, 4, on my new graph I'm going to have 4, negative 4. Ooh, switch colors. And if on my inverse I have negative 1, negative 1, what happens when I switch the x and the y coordinates here? I still have negative 1, negative 1. And here on my original graph I have 1, 3. So on my inverse graph I will have 3, 1. And finally, on my red graph here, I've got the point 3, 2. So on my inverse graph, I will have 2, 3. Finally, we need to connect our dots. These two are connected, so that means these two are connected. These two to these two to those two. And if we look at the graph that we got in the end, can you see that it has been reflected perfectly over the line y equals x? Now, for whatever reason, it's harder for our brains to reflect over a diagonal line than it is to reflect over a horizontal or a vertical line. Right? It's pretty easy to take something and flip it horizontally, right? But to kind of turn your head and try and flip it over a diagonal line is a little bit harder to see. But there's a way that you can cheat on your final exam and they'll never know. If you take your page, I don't know if I should be recording this, and you turn it so that your diagonal line ends up being a horizontal line, can you see that it would be easier to see? Like, so here we go. Let's see how that would look. I'm going to take so here's your graph. You take your page and you turn it so that that dotted line is now horizontal. can you see that flipping up and down the red graph matches perfectly with the green graph, right? And the teacher comes by, you just straighten your paper again. Nothing ever happened. It's not cheating. You're disappointed. A little bit. So if you do that, you can see that reflection. That this point went straight down to this point goes straight up to this point, and everything's been reflected over. This isn't on our quiz. Our quiz tomorrow is just on section 3.1 to 3.3. This will be on your quiz on Friday. Yeah, I'll put that up later. But thanks for reminding me. Okay. So, a couple of other important things to notice. Did you notice that this point didn't change? Why didn't it change? Because the x and the y are exactly the same, right? And when you switch them and it's right, you notice that it's right on the line y equals x. So this is another point that didn't change, even though we didn't label it. But we have to be careful when graphing that wherever our line y equals x is, any points on our original graph that touch that line have to stay the same for the inverse graph. Part B says, is the inverse a function? Do you remember how to tell if something is a function or not? No. Perfect. There is a test to tell if something's a function or not, and it's called the vertical line test. And the way that the vertical line test works, write it down, vertical. If you move your vertical line from left to right, does it ever touch a graph more than once? So if we go through the red graph, see how it's just touching the red graph at 1 point, 1 point, 1 point? It's touching it at 1 point all the way through. So we can say that the red graph is a function. Yeah. But if we take that vertical line test and go through the green one, here we run into a problem. It touches the green graph more than once. In fact, here's a spot where it touches it 3 times. But you just need to find one spot somewhere where it touches more than once, and it will not be a function. So we can say the inverse is not a function, which means you would not be allowed to use this notation for the inverse, because that notation is only for an inverse function. And this course is really particular about how we write things. And finally, state the domain and range of the original and the domain and range of the inverse. I haven't done interval notation for a while, so I will this time. My smallest x value is a -4. My biggest x value is a 3. My domain goes from -4 to 3. For my range of my red graph, my smallest y value is a -1, and my largest y value is +4. On my green graph, domain and range, my smallest value, x value on my green graph is -1. Largest value on my green graph is +4. We use square brackets in interval notation because those values are included. And in my range, my smallest y value on my green graph is -4. My largest y value, my largest y value on my green graph is +3. Compare the domains and range. What do you notice? They just got switched, right? This one, the domain, became the range, and this one, the range, became the domain. Why? Because the main idea of an inverse is that you switch x and y. So if the domain were all my x values of my red graph, if I switch x and y, all my x values become y values. And so my domain becomes my range. And my range, all my y values get switched to my x values. My range becomes my domain. So you could get in a question on the exam that says, the domain of g of x is -4, 3, and the range is -1, 4. What's the range of the inverse? And then you'd have to say, oh, I just switch x and y, so my domain becomes my range. Okay, try questions 4 and 9.